Okay, I want to solve a harder problem using 3 different techniques to give you a chance to watch carefully how we tackle problems like this. We begin with an unmarked police car traveling at a constant 95 kilometers per hour is passed by a speeder traveling 140 kilometers per hour. Precisely 1 second after the speeder passes, the policeman steps on the accelerator. If the police car's acceleration is 2 meters per second squared, how much time passes before the police car overtakes the speeder? It takes some practice before you really know how to tackle a problem like this, but after I show you this one, you'll probably be comfortable with problems in which one object catches up with the second. The first step is to change the kilometers per hour to meters per second. So to do that, you multiply by 1,000 to get meters and divide by 3,600 to get seconds, and you get 26.39 approximately. 26.39 meters per second. Can you read it now? And 38.89 meters per second. Okay, so that said, here's how we get started. We imagine that the police and the speeder are side by side at one moment in time. This is when the speeder passes the policeman. And from this moment forward, both of them move forward from this point with the speeder pulling ahead, initially pulling ahead of the policeman. So, if we look a moment later, the speeder is now ahead of the policeman, and eventually this gap widens for a while, and eventually the gap starts to diminish as the policeman accelerates, and eventually the policeman catches up and they are at the same place at the same time. Okay, at this point they have the same displacement at the same time. Using that information, we're going to try to write an equation that says as much, and then solve the equation. So here's the tricky part for some people. What's the equation that I need to write down? How do I start? Let's keep track of how far the policeman goes. So the policeman initially, for the first second, is just going 26.39 meters per second. So the delta x of the policeman, the displacement of the policeman, is a 26.39 meters per second times 1 second. That's how far it goes in that first second. Then we're going to tack on how far it goes in remaining seconds. What I'm using right here, of course, is just the fact that delta x is v average times t. Okay. After the first second, his displacement is now determined by this equation. Delta x equals vit plus 1/2 at squared, because he is now accelerating from some initial velocity. He doesn't have just a constant velocity, and we don't know his average velocity. We use this typical kinematic equation to calculate how far he goes. So t is the unknown variable here. We're going to try to figure out how long it takes for the policeman to catch the speeder, but right now we leave t as a variable, and we say that beginning at 26.39, we have 26.39 meters per second times t. Okay, and then we tack onto that plus 1/2 times acceleration, which is 2.00 meters per second squared, t squared. This entire expression right here, okay, needs to be set equal to the delta x of the speeder. because that's the condition under which they meet up, when they both have the same overall delta x or displacement. It happened here, of course. They were at the same place here, and then it happened once again here, and we're solving for the second one, of course. So the delta x of the speeder is easier because it's just going the same speed the whole time. It's just v average times t. It's just 38.89 meters per second times the time. Now this point is very important. So the policeman went t seconds after a 1 second delay. The speeder was going this for the entire time, so that's a total of t plus 1 seconds. It's important to realize that this is one more than this. If this is 5 seconds, then this has to be 6 to be the total time. Now we set these two things equal to one another. So we say, and I'm going to drop the units just because it gets tedious and it's going to make it easier to make a mistake. We have 38.89 times t plus 1 equals equals 26.39 times 1, or just 26.39, plus 26.39t plus 1/2 times 2, but 1/2 times 2 is just 1, t squared. We have a quadratic equation, okay, and we can distribute this term here and get 38.89t plus 38.89 equals 26.39 plus 26.39t plus t squared. We can now simplify this equation. If I move everything over to the right side, we have a 26.39t. I'm going to subtract 38.89t from both sides, and this becomes a negative 12.5t. I have a 26.39, I subtract just a 38.89, and I get a negative 12.5. This is a quadratic equation that we can solve. It's basically of the form at squared plus bt plus c equals 0. And to solve it, we need to use the quadratic formula. So we are going to use t equals negative b plus or minus the square root of b squared minus 4ac all over 2a, given that the implied 1 in front of the t is our a, this negative 12.5 is our b, and this negative 12.5 is our c. So we plug in a negative 12.5 for a positive 12.5, plus or minus the square root of b squared, so a negative 12.5 squared, minus 4 times a, which is 1, and c, which is a negative 12.5, all over 2 times 1. This simplifies down to 13.43. We use the plus sign when we simplify this down. Otherwise we would have ended up with a negative time, so you just choose it because it's the only one that makes sense. You end up getting t equals 13.43 seconds. So the police car was accelerating for 13.43 seconds after having gone a constant 26.39 for 1 second. In total, this entire chase took 14.43 seconds. There was the initial 1 second and then an additional 13.43 seconds for a total of 14.43 seconds. That's how long it took after the speeder passed the policeman for the policeman to catch up. So that's the answer. Now let me show you other ways of doing it. Okay. So again, imagine that we have the police and the speeder, and after a little bit the speeder is now pulled ahead, and at some point they catch up again. Okay. And the policeman initially is going 26.39 meters per second, and the speeder initially is going 38.89 meters per second. Now what we're going to do is shift our perspective. This is an exercise in relative motion. We're going to change our point of view, and by doing it, it makes the problem a little bit easier. See if, even if you haven't heard of this before, see if it might make sense. From the point of view of the policeman, this car doesn't appear to be going 38.89 meters per second. It appears to be going 12.5 meters per second, 12.5 faster than the policeman. If the policeman was in a very smooth riding vehicle, he might even forget that he's moving. He looks out and he clocks, or he sees the speeder moving 12.5 faster than himself, moving away from himself at a rate of 12.5 meters per second. We are allowed in physics to change our point of view. In this case, this is equivalent, these two speeds are equivalent to saying that the policeman is not moving and the speeder is moving at 12.5. Or rather, really, this is just 12.5 larger than 0. So again, we are changing our point of view. We are subtracting off 26.39 meters per second from both numbers, and we're saying this one is 12.5 faster than this one. If that's confusing, you probably should look at a few more examples. It's really helpful to get comfortable with this. Regardless, you can still watch me solve this problem because the math is cleaner. It's a little bit easier. Okay. So it's basically like the policeman is at rest for 1 second, and then after that 1 second starts to accelerate at 2 meters per second squared. I'm going to redraw the picture to try to make it a little bit easier. So here's the policeman. Here's the speeder having already pulled ahead. In that very first second, this much distance opens up. In that very first second, well, 12.5 meters opens up. Because in 1 second, at a rate of 12.5 meters per second, this pulls ahead by 12.5 meters. Now, in the remaining time, this speeder moves ahead some additional distance, and the policeman has to go that entire distance. How far does the speeder go? 12.5 times t, where t is the number of seconds. How far does the policeman need to go? well, the same distance, but to calculate this distance, we use this kinematic equation, realizing that now in this new frame of reference, VI is 0. Therefore, the delta x, this distance, is just going to be 1/2 times a times t squared. 1/2 times a times t squared, which simplifies to just t squared. That's a distance. Basically, this t squared has to equal the 12.5 t plus the additional 12.5 meters. This is the equation we saw earlier, t squared minus 12.5 t minus 12.5 equals 0. Again, we saw this equation earlier. We can solve it. We get t equals 13.43 seconds. We tack on that extra second, that corresponds with this 12.5 meters, for a total of 14.43 seconds. Changing the point of view, or the reference frame as it's called, allows us to solve the problem a little bit faster. Maybe it's not that much different. And here's one last way that might be the best way of all. Graphically. So remember that the area under a curve on a velocity graph equals the displacement of the object. So let's represent these two vehicles on a velocity graph and then see how we can use a graphical method, well, a mixture of the graph and the math that goes with it, to solve this. So the speeder is going, say, a constant 38.89 for some period of time. And the policeman is going 26.39 for 1 second, until he begins to accelerate. He accelerates at a rate of 2, so therefore I need a slope of 2 now on this graph. A slope of 2. So I'm just going to estimate. It doesn't matter about the drawing, really. It doesn't matter about being accurate. So this is 26.39 meters per second. And now this slope, the rise over run, delta V over delta T equals 2. Now at some unknown time, we're just going to label it T, these areas have to equal each other. So the area under this, under the 38.89, that area has to equal this area. It goes all the way up here, this entire area. Those two areas will be equal when the two cars have equal displacements, and that is the time at which the policeman catches up. So with this graphical method, we just need to write down an equation that says one area equals the other area. So the area of this rectangle is easy to calculate. It's just base times height. That is, it's t times 38.89, or 38.89 t. Okay. And now this other area can be broken down into a rectangle and a triangle. So here's the rectangle. And for the rectangle, the area is 26.39 t. And now for this triangle up here, its area is 1/2 base times height. 1/2, the base, notice, is t minus 1. And what's the height? The height, which is delta V, is going to equal 2 times the base. So the base times 2. The base times 2 is the height. Now we can clean this up a little bit. Over here the 1/2 and the 2 will cancel as we multiply all 4 terms together. The t minus 1 and the t minus 1 multiplied out equal t squared minus 2t plus 1. Okay, and we end up getting, well, negative 12.5t plus t squared minus 2t plus 1 equals 0. Negative 12.5t and negative 2t equal negative 14.5t plus t squared. Can I put the 1 here? Thank you. Okay. So again, we arrive at a quadratic, and all these methods are requiring solving a quadratic using the formula, and that's kind of annoying, but that's what's happening. So now, again, we just say t equals negative b, negative the term in front of the t term, or the coefficient in front of the t term. So negative b plus or minus the square root of b squared minus 4a. A goes in front of t squared. It's an implied 1. C is also 1. All over 2 times a. Okay. And when you solve this, you get 14.43 seconds. There's no tacking on 1 to this number. This number is the final time. The way we set up the problem, this number is the final time. And so this graphical method is a pretty easy way of finding the time. It might be less confusing than the other methods. You can see pretty well what's happening. Okay, and here's our final time. Okay, that's it.